Okay, back again with helps for reflection transmission at oblique incidence. So for problem 8.19, we have a wave striking a prism, which is something like this. And then we have some transmission, reflection, more transmission, and then another prism, transmission, reflection, and finally the wave exits. And we're trying to find the power ratio. So what we're trying to find is the E squared over 2 eta naught at the output, and that's going to equal something which is in terms of all the transmission and reflection coefficients. To simplify the notation, I'm going to call the air 0 and the glass medium 1. So here's how this works. At the first interface, we have a tau from 0 to 1, and then we have a reflection coefficient from region 1 to region 0. So we're in the glass, and then we reflect within the glass. We'll call that gamma 1, 0. Then we have a transmission from tau from the glass to the air. And then here we have a transmission from air to glass. Here we have a reflection coefficient from glass to air. And here we have another transmission coefficient from glass to air. So the 1s and 0s give you the ordering of the etas in the reflection and transmission formulas. Now, how do we put all those together into a power ratio? Well, when we get the first transmission, we pick up a transmission coefficient, but we're dealing with power, so we square it. Then we have a reflection coefficient all squared. And we have the next transmission. Now we're back into air. Then we have the prism, the second prism. And then we have a gamma 1, 0 squared. And finally a tau 1, 0 squared. And then all that is in terms of the E incident magnitude squared over 2 eta naught. So the power ratio is all of this, and that's what you'll be calculating. Little tip on this problem, something sort of special and magical happens for the two reflections, and you'll see that when you try to run the numbers for those reflection coefficients. Something interesting happens. So that's some tips for 8.19. Now for 8.20a, for this problem it's really useful to know something about K diagrams. A K diagram is a way to sort of graphically understand the wave vectors in the two materials. So we'll draw a little semicircle with radius k1, and then we'll draw another semicircle with radius k2. The reflected wave vector is a vector of length k1. Incident is the same thing, but down here, a lot of times in K diagrams, we only draw the reflected K vector. We only need one of them. And the transmitted K vector is a little more shallow, and that has length k2. And because k2 is longer, that vector is a different angle. So we have a little bit of difference between the incident and reflected directions. Because of the boundary condition, we have to have a phase matching condition between the electric and magnetic fields on the boundary, which means that K1x and K2x, those are equal. That comes from the boundary condition. We call that phase matching condition. And when we write that down in terms of angle sign, the signs of the incident and reflected and transmitted angles, that is called Snell's law. Now, when we have a multi-layered material, like in this problem, each time we go from one material to the next, we have equality between all the x components of the K vector. So we'll end up with something like K1 sine theta incident is equal to K2 sine theta 2, the angle of the wave vector in region 2, and so on. And that string of equalities relates the phase matching condition across each interface to the stack of materials. And that allows us to relate the last angle to the first angle, and you can solve the problem that way. That's a tip on 8.20a. For 8.23, now we come to total internal reflection. So I'll write TIR up here, so you know we're talking about total internal reflection. Now in this case, we're going from a more dense material to a less dense material. So epsilon 1 and epsilon 2 are related in this way. That accounts for the I in internal reflection. The wave is coming from a material like glass or whatever. This might be glass, let's say, and this would be air. We're going from the more dense to the less dense material. Now let's look carefully at the K diagram. We draw a circle with a larger radius corresponding to the larger value of K2 of K1, because epsilon 1 is bigger. And then we draw a smaller circle with a radius K2 with epsilon 2 in it. Now, if we have a shallow incidence angle, we have the incident wave vector here, the reflected wave vector there. Because of the phase matching condition, the x components of the reflected and transmitted wave vectors have to be equal. That's what the dotted line is saying. Now you can see that the refraction sort of happens away from the normal direction. So that's characteristic of going from a denser optical material to a less dense. We sort of rotate away. If we're going from air to glass, then we would have something like this. The refraction is sort of towards the surface normal. Anyway, when we're going from the more dense to the less dense material, if I increase the incidence angle a little bit, let me clear out my picture. So let's say our incidence angle is something like this. Well, something special happens at that angle. If we draw a dotted line, we find that K2x has to be exactly equal. Let's see, K1x has to be exactly equal to K2. If we try to go to a steeper angle than that, then things become different. That's total internal reflection. Now, right where this dotted line just meets the semicircle on the right, that's what we call the critical angle. And total internal reflection happens at any incidence angle that's sort of steeper than that critical angle. Well, right at the critical angle, we have K1x, which is K1 sine theta incident, equals to K2 sine theta t. But from the K diagram, theta t is 90 degrees and sine theta t is 1. So you can use this relationship for the critical angle to solve 8.23. Now, at this point, it's really interesting to consider what happens if we go beyond the critical angle. So now we have our semicircle with the smaller value for K2. If we try to go to a really steep angle, we have the incident and reflected K vectors. The x component of the transmitted K vector is as big as it can be. It's equal to K2, but somehow we have to have K2x squared plus K2z squared is equal to K2 squared. That's the dispersion relation for the right medium, or medium 2. Well, K2x sorry, that should have been a little bit longer. K2x beyond the critical angle is a little bit bigger than K2. So if this value is bigger than the value on the right, then K2z has to be negative, which means that Kz is imaginary, and all sorts of interesting things happen in that case. In fact, the z part of the phasor form of the wave in medium 2 has an e to the minus K2z times z in it. This is imaginary, so when we put everything together, we get an e to the minus alpha z, which is like what we had in a lossy material, only there's no loss. That is a very special type of wave called an evanescent wave. Evanescent waves have a lot of applications. In fact, the mathematics of evanescent waves is really similar to quantum tunneling. If I have a more dense material here and air or less dense material than the more dense material, I can have a wave that goes at a steeper angle than the critical angle. It's evanescent, and I'll draw that using an exponential decay, and it can become a real wave again in another material with a finite size gap, and that is sort of an optical or microwave analog to quantum tunneling. So if you've ever heard of quantum tunneling, particles going through some kind of a barrier they shouldn't be able to penetrate based on classical physics, that's really related to total internal reflection in this idea of an evanescent wave, which I'll write out just so you can see the word written out. So that's an evanescent wave. Okay, let's clear that, and we will look at 8.27. This problem is fairly straightforward, so I won't say a lot about it. All of the incident, reflected, and transmitted electric fields have a y hat in them. The H fields, the easiest way to get that for this problem normally is to use k hat cross E over eta, and you'll figure out k hat from the wave vectors, turn it into a unit vector, work the cross products, and that will give you the magnetic field. So the problem, it's a bit tedious, but doesn't involve anything more than these plane wave formulas from earlier material. Now we are on 8.31. This is a Brewster angle problem. So the Brewster's angle occurs when gamma is equal to 0. Now for parallel polarization, that means the numerator of the reflection coefficient has to be 0, which means that we have eta 2 cosine theta reflected is equal to eta 1 cosine theta incident. Sorry, that should be a theta transmitted, a t. That's the numerator of the parallel polarized reflection coefficient for oblique incidence. If we have equality between those two things, then the reflection coefficient is 0, and you can use this relationship to solve the homework problem. Now for perpendicular polarization, we can only have that equal to 0 in the case where mu1 is not equal to mu2. So for non-magnetic materials where those are equal, we don't have a Brewster's angle. We only get that for parallel polarization. And there's a discussion in the lecture notes of the physics of that. That brings us to the last problem. For this problem, we're really just computing the reflection coefficient and transmission coefficient. The steps for that is to find, go from theta incident and find from that theta reflected and theta transmitted. And then we plug that into the formulas for gamma and tau and outcome values. I find it helpful to use MATLAB and Python because for me the calculator work is a little bit tedious, but it certainly can be done on a calculator. And that is it.